Hi, hi. This is our continuation of the discussion of indexes of B plus tree indexes inside PostgreSQL. This time let's quickly switch over and directly switch over to the terminal because we have found indexes to be really super awesome and helpful. And the index scan that we can perform with the help of indexes really can speed up query evaluation big time. So I was so thrilled about using indexes that I've created many more of them already. So I have the index table, it's a 3-column table. I've already got an index on the A column. So as you can see here, I've already created two more indexes on the B column and on the C column. You see here a B tree over the B column, a B tree over the numeric C column. All right, let's not focus on this particular addition here. All right, so these are B tree indexes over the B and C columns. All right, so I've already created them. So let's see what's going on here. There you go. All right, so there is the A index, the B and the C index. All of these are B tree indexes. I have created these. This has been created because A is a primary key. Let's not focus on this word cluster right now, but we will come back to it in a minute. Okay, so much. This is situation now for our index table. Let's quickly run this analyze command, so that PostgreSQL is informed about these two indexes and takes them into account when we run future queries. So analyze the index table. This went very quick, 1 second. Okay, so we are all set. 3 indexes, 3 columns, all of them are index supported. Let's see. So let's run. Let's run a selection query over the C column with our brand new indexed C B tree index. And let's see what comes out of this. This should yield an index scan, because this is a rather picky predicate, I would say. Let's see. We will see that in the analyze output. Okay, so what have we got here? No, this is not an index scan. This is a bitmap index scan, and it's only one of 2 operators. The bitmap index scan is connected. It feeds its output into a bitmap heap scan. All right. So this is unexpected in a sense. At least the indexed underscore C column index is involved in the operation. This looks good to me. So the system has indeed picked up the presence of the index.c index. This is the promise of the declarative SQL language. We don't have to mention that particular index explicitly in the query here. It's going to be picked up automatically, and this has happened. But a bitmap index scan has been performed. I've never seen that operation before. And as you can see, the system was actually estimating a rather low query result. So it has detected that this predicate here is indeed picky and selective, and it indeed turned out this way. 3,531 rows of 1 million only have qualified here. That should qualify as a selective predicate, and index scan should have been used here. So, what's the reason what's the reason behind that behavior? Let's discuss this. For that, let's switch over to the slides again. All right. So there's 2 different situations shown here on the very same slide. Let's first look at the situation on the left-hand side. And this is the positive, the good piece of the discussion. All right. So what I'm depicting here is the use of an index to evaluate a range predicate. All right. So we would enter the index at the root and descend through its search tree structure until we hit the leaf level, the sequence set. And the sequence set, of course, would be scanned not in its entirety, but only as part of it would be scanned from the low to the high borders here. Okay, so that looks good to me. While we scan this particular part of the set, we would find index entries in the leaves, and we would follow their rids. We would follow the rids into the heap file. And as you can see, while I scan this sequence set from left to right, I will first hit this page, and then this page again, and then later the next page, only one entry there, and then the next page in this in the heap file. Adjacent pages. I will hit adjacent pages in the heap file. In this page, I will even pick up 3 matching records and so on and so on. All right, so I will walk the sequence set from left to right. I will also walk the heap file from left to right effectively, because it appears that the heap file obeys the same ordering, the same order as the sequence set does. We know the sequence set is ordered for sure. It's in ascending order of the index column values, of the index key values. It appears the heap file has the same ordering. So you see the smallest entry that we found during the heap scan lives here on the left. The next larger lives just adjacent to that to the right. The next larger lives here. The largest value lives to the very right of the pages that we've accessed here. The order that we encountered the keys in a sequence set appears to match the order of the keys in the heap file. This leads to this very ordered and very neatly organized heap file access pattern that we see here on the left hand side. Okay, and this is the situation of 1. Okay, this situation, thumbs up. The order of the leaf entries is the same as the row order in the heap file. All right. Another situation could be situation 2. Again, we would start our descent from the root page through the tree to the sequence set. The left-hand side of the part of the sequence set that we now need to scan has been found, and everything is the same. This is just the same range of sequence set that we need to scan. But now see what happens. The pointers that we find here, the red pointers that we find in the index entries, first lead us to this particular page. Then the next entry will lead us to this page. Then the next entry will lead us to this page back again. Then the next entry will lead us to this page, and we will then be led to this page again, and then to this page and to this page. This is really a chaotic page access behavior. It's actually random I/O that we are performing here on the heap file. Okay, access some page here, then there, then over there, then come back here, pick up one row here, then later pick up one row there, come back to this page to pick up another row. This is just random I/O behavior on the heap file from the viewpoint of the heap file. So the sequential scanning, the very orderly scanning of the sequence set, leads to such random I/O behavior on the heap file. This is actually sequential I/O behavior on the heap file. We will first access this leftmost page, then its adjacent neighbor, and so on. This is just sequential scan. This is jumbled mess. Okay, and of course, this is a result of non-matching order regarding the keys of the sequence set and the row order inside the heap file. The two orders were matching here. The two orders of the key order and the row order inside the heap file, they do not match, and they lead to this rather unfortunate random I/O behavior that we are observing. And this is actually the case. This is the cause. The root cause for the non-use of the index scan that we've just seen. This is the cause for the bitmap heap scan and bitmap index scan pair that we have seen in the plan just before. Okay, so let's switch back to the editor to make this more clear. All right, so let's now compare the good and the bad situation, the left-hand side and the right-hand side of the scenario, and let us replay that here on the PostgreSQL side of things. All right, so the good case, the left-hand side, the orderly access to the index pages, is actually represented by this query here. This is just a selection query with a half open range query, so that's very efficiently supported by B+ trees. Okay, we will of course use the B+ tree over the A column here. All right, and we will select 3,531 rows regarding this particular predicate. Okay, so this is the selectivity or the pickiness of this particular predicate. If we evaluate that, Then we see an index scan. An index scan has been used, and indeed 3,531 rows have qualified. This is a rather picky predicate. We expected that the index scan would be used. All is well, perfectly fine. Now this again. This is a predicate that has the exact same selectivity. So we have already seen that at the beginning of the video. 3,531 rows will qualify regarding this particular predicate. So the selectivity or the pickiness, this is not the difference between the two scenarios here. But let me evaluate that. And we will indeed again see the bitmap index scan and the bitmap heap scan pair. The bitmap index scan has indeed identified the 3,531 rows. All right. What has happened though is that this is not the end of query evaluation. This is not the end of query evaluation. This is one first phase of query evaluation, and we will show what phase is implemented by bitmap index scan and which subsequent phase is implemented by bitmap heap scan in the next video. All right. So, but there's some disappointing news here in this plan, which says that to load 3,531 rows, from the indexed table, the plan led to 2,964 block accesses. Heap block accesses. Heap block access is in this case accesses into the heap file, into the indexed table file. All right. So this many rows have been retrieved, but this many blocks have been accessed. So that's a ratio of 353. Okay. Divided by 29. Let me check again. 64. Well, that's about 1.2, not less than 1.2 rows have been found on each page that has been accessed here. So lots of page accesses for really very few accesses, very few rows that have actually been identified by this query and returned to the user. Okay. All of this is indeed due to the fact that the ordering of rows, that the current ordering of rows in the heap file matches the A order, the order in the sequence set of the B plus tree index over column A, much better than the C order. All right. So it appears that the pages inside the heap file appear to be ordered according to the A values, but not ordered according to the C values. And to test that hypothesis, let's actually check that. Let's actually check that. I've brought a function with me, an auxiliary function that can turn a RID into its page number. So effectively it just projects the slot entry away. So if this is my page number, my row ID, I'm sorry, consisting of a page number and a slot ID, what the page of function above will do, it will just discard the S and will just return the P. So please extract the page number from the row ID. This is what this function page of does. Okay, I've defined that. So what we will do now, we will repeat our query on the index table, and we will use the A predicate, and then we will measure on how many distinct pages, will I find the matches. How many distinct pages carry the rows that qualify this particular predicate. And you see this is the aggregation that will count this distinct number of pages. Okay, so for all qualifying row I will just access its row ID. I will extract the page on which that row lives and then count the distinct pages on which I found all the matches, all the 3,531 matches for this particular query. I will also print or output the span, so the minimum and the maximum, or the leftmost and the rightmost page, in a sense, in the heap file that are carrying the results of this particular query. Okay, so let's do that. Let's evaluate that for the case of the predicate on column A. Okay, so it appears that indeed we have accessed 33 pages, 33 distinct pages on which we found the matching rows, and all of these have indeed been adjacent to each other. Okay, all of these have been adjacent to each other. The span between the leftmost and the rightmost page is just 33, and we have only accessed 33 pages. All of the pages that we have accessed are adjacent to each other. This looks like that the index access have actually led to a cool sequential I/O or compact I/O on very few pages on the heap file. This is the good case. All right, so if we repeat this experiment with the comparison on the C column, okay, this is again the predicate that will return 3,531 rows, so selectivity is not the issue here. Then also let's measure on how many different pages we will find these rows, and where are they located inside the file, at the beginning of the file, at the end of the file, hopefully in some very compact region of only, say, 33 pages, as in the case just seen. That would be awesome. All right, so let's see what happens. Whoa, okay. So the 3,531 rows that we've returned are indeed found on 2,964 distinct pages. Oof. This 2,964, we have seen that before. This has been the output here. This is indeed the number of pages that needed to be accessed to collect all the matches. Okay, so there is no clustering. There is no portion of the heap file of our index table in which all the values that carry the or that fulfill the predicate I.C equals 0.42 can be found. They are indeed spread all over the file. The file only has about 9,346 pages or something like that. The matches are found all over the file. This really leads to the chaotic access pattern that we have seen in on the slide, on this particular slide here. Okay, so this would describe the case when we select regarding column A. This would be the case when we select regarding column C. Okay, and we need a different operator. We need a different index scan operator that can efficiently handle this really tricky situation. And this is the Bitmap index scan, the Bitmap heap scan pair. And as I told you, we will come back to the details of that when we produce the next video. Okay, first let's more deeply look at what we've seen here. What's happening here? What's so special about the sort order of the index entries and the sort order of the rows that is present here in the heap file? And this is exactly what is described by clustered and non-clustered indexes. So the good case, the left-hand side case, the column A case, is described by the notion of clustered indexes. When I'm talking about an index I that is organized over some column A of a table T, and the row order in the heap file. The row order in the heap file for column T coincides with the order of the keys with the A order inside the sequence set of the index. So this is the crucial notion here. All right. So if I find two entries in the sequence set of my index, and I'm looking at two different key values here, and ki is smaller than kj, all right, then there is also a correspondence on these pages inside the heap file that they're associated with. Then this key order is also reflected by the page order. The heap file is sorted according to the keys that are being indexed by my index I. All right, so that would be the situation of a clustered index. Index sequence set order is compatible, coincides with the row order inside the heap file of table T. Okay, when we scan such a clustered index, then it will collect matching rows from adjacent heap file pages. So if I perform my scan and scan from ki to kj, all right, so I'm scanning from smaller to larger key values, I will scan the file, the target file, the heap file of the table T in a left to right sequential order. That's perfect. It will lead to sequential I/O. I will also find on each page that I load from the heap file of table T, on each such heap file, I will find many matching rows, because these rows rows with adjacent key values live on adjacent pages, maybe even on the same page. As we've seen on the in the terminal, all of the 3,531 rows that we found regarding the predicate on column A, they all lived on only 33 pages. This is the awesome situation. So we have to perform sequential I/O, and we have to perform less page I/O because each page carries a lot of hits. Okay, this is the situation of clustered indexes, and we like that. There's the sad fact that the non-clustered indexes are the majority. Because there's only one sort order that we can arrange the rows inside a heap file for table T. Once we have decided on one particular sort order, maybe regarding the A column, then the index on the A column will be a clustered index and it will benefit. All other indexes, the index on column B, the index on column C, all of these will be non-clustered. So the order of the keys in the sequence set of these indexes, which of course will still be sorted, these are ordered indexes, they will not coincide, they will not match the row order in the heap file. The heap file is sorted regarding column A, then it cannot be sorted regarding column C, in the general case at least. Okay, so scanning such a non-clustered index will find matching rows regarding the C predicate, for example, potentially scattered across all of the file. All of the pages could potentially carry matches or hits regarding this particular predicate on column C, for example. Okay, so that leads to random I/O. So maybe it's a page near the end of the file, then the next hit may be near the beginning of the file, and so on, and we may perform really crazy jumping while we perform the very ordered heap sequential set scan, but this will lead to random I/O accesses into the heap file. Okay, because the rows that have adjacent C values are not to be found adjacent on the pages of the heap file, this also means that once we have accessed one heap file page, we will probably only find very few matches on there. As you've seen in our calculation, in the case of the selection on the I.C column, we only found about 1.19 rows per page. And that's a really bad ratio. So we will have random I/O scattered across all of the files, and we have lots of page I/O because each of the access pages will contain very few matching rows only. These are both bad news. And a normal index scan cannot cope and cannot account for this particular observation and situation. We need a special technique for that. We need a special pair of operators to deal with this situation, and this is the Bitmap index scan and the Bitmap heap scan pair. What they will effectively perform is a form of RIT sorting. So before we perform really chaotic and crazy random I/O accesses into the heap file, we will take our time and organize the RIDs that we have to access to evaluate the query in some orderly fashion. And once we've done that, only then we will actually perform the actual accesses into the heap file. All right. And this two-stage process is embodied by these two operators, and they will rectify, at least to some degree, the sad situation that we have with non-clustered indexes. The details of that are to be found in an upcoming video. I hope you will be around when we explain the bitmap index and heap scan twins. All right, see you then. Bye.